6.3 Arc length. Let's use a real-life situation to introduce this topic. An osprey, flying at 15 meters a second, at an altitude of 180 meters, accidentally drops its prey. The parabolic trajectory of the falling prey is described by the equation y equals 180 minus x squared over 45, until it hits the ground, where y is the height above the ground and x is the horizontal distance traveled in meters. Calculate the distance traveled by the prey from the time it is dropped until the time it hits the ground to the nearest tenth of a meter. Now in this problem, we are finding the length of this arc. So how can we find that length? Before we solve that equation, let's look at a quick derivation of the arc length equation itself. Now we know from the past that the distance equation is described as x2 minus x1 squared plus y2 minus y1 squared, all under the square root. That simplified is just the square root of the change in x squared plus the change in y squared. If we wanted to look at every point between the distance of 2 points, we would describe that as the sum of as many points as we need when I equals 1 of the distance equation. Now, through magic math, which is really just pulling the change in x squared out, you come up with an equation that looks something like this, which has the slope or the derivative in it. Now, if you want to find all the points with that equation, you just simply do the same thing we did earlier and have the sum of all the points of n. Or to be more exact, if you want every point, you take the limit as n goes to infinity. And that's where the arc length formula comes in. If you take the integral between 2 points of this derivation of the distance formula, you get the length of an arc of an equation. Using a visual derivation, if you take the length of an arc and you split it into equal parts, the more parts you split it in, the more accurate the length of your arc will be. The most accurate is going to be all the points on that arc, obviously. Let's start with a simple example. Example 1. Set up, but do not evaluate, an integral that represents the length of the curve. The curve we'll be using is y equals the cosine of x. The limits that we're given are 0 is less than or equal to x, which is less than or equal to 2 pi. Now the most important component of the arc length formula is this derivative. So the derivative of cosine of x is the negative sine of x. So, because the question asks to set up an integral, the integral we'll set up using the arc length formula is the integral between 0 and 2 pi of the square root of 1 plus negative sine x squared dx. Let's attempt a more complex example. Example 2. Graph the curve and find its exact length. The curve we're given is x equals y to the 3 halves, with the limits 0 is less than or equal to y, which is less than or equal to 1. Now it's important to note that it must be in terms of x to graph. You cannot graph y to the 3 halves. Also, you must plug y into the arc length equation, which means you're finding the derivative of x, you're not finding the derivative of y. So, the derivative of x in terms of y is 3 over 2 times the square root of y. Now, plugging that into the arc length equation, you have the limit between 0 and 1 of the square root of 1 plus the derivative, which we just found, squared. That simplified is just the limit between 0 and 1 of the square root of 1 plus 9y over 4 dy. That, when plugged into your calculator, gives you 13 root 3 minus 8 over 27, or about 1.440. The accumulation function is another important aspect of the arc length formula. The accumulation function is used to find the distance along a curve from any point A to any point x. This is modeled by the length equals, or the distance equals, the integral between any point and any point, so a to x, of the square root of 1 plus the derivative of f of x squared dt. Now, if we look at an example, find the function for the arc length of the curve y equals 2x to the 3 halves starting at 0, 0. So let's set up the equation for arc length using this new accumulation function equation. So the length of x is equal to 0, because that's where you start, the integral between 0 and x of the square root of 1 plus 3x to the 1/2 squared, the derivative of 2x to the 3/2. That simplified is the integral between 0 and x of the square root of 1 plus 9x dx. To solve this integral, we must use u substitution. So let u equal 1 plus 9x. That means du over dx equals 9 and du equals 9 dx. So going back to our integral, let's integrate this equation without using our limits yet and just see what it looks like. That equals 1 over 9 times the group 1 plus 9x to the 3/2 over 3/2. Putting our limits back in, we have 2 over 27 times 1 plus 9t to the 3/2 with our limits of integration between 0 and any number x. That means our function and the answer to this problem is 2 over 27 times 1 plus 9x to the 3/2 minus 2 over 27. We have all the essential tools needed for the arc length equation. Let's go back to the Osprey problem from the beginning of the lesson. So you have this parabolic equation, y equals 180 minus x squared over 45, and if you remember, that is the fish dropping from the bird. So you have this equation. The most important part, remember, is to find the derivative of the equation itself. The derivative of this equation is negative 2x over 45. Also, in this equation, you must find the limits of integration for your integral. In order to do that, you must make y equal to 0 and solve for x. When you do that, you get x equals 90. So you have a is 0 because you're starting at 0, and b is 90. So, using our arc length formula, the equation is the integral between 0 and 90 of the square root of 1 plus negative 2x over 45 squared dx, or about 209.1 meters.